Okay, we just finished part two on chapter 15 on buoyancy. We're going to go on to part three on Archimedes' principle. And let me dismiss my image and um, discuss Archimedes' principle. Um, Discovered by the Greek scientist Archimedes, relates buoyancy to displaced liquid. And it states in bold here, an immersed body, completely or partially, uh, is buoyed up by a force equal to the weight of the fluid it displaces. And it applies both to gases and to liquids. The famous story is that while he was in a bath, as he got into the bath, he saw the water rise and displace a bit, and his task was to find out if a crown was made of pure gold. And of course, it's hard to measure the dimensions of an irregular object like a crown. So his task was to figure out how much, what was the volume of the crown, so he could see if the density indicated that it was pure gold. And he didn't know how to do that. But when he got in the bath and saw the water rise, he figured, oh, I can put the crown in water and figure out its volume and therefore get its density. And so he supposedly jumped out naked from the bath, going through the streets yelling, "Eureka, Eureka," which translates, I found it. I found the method of measuring the volume of the crown. Whether that's a true story or not, I don't know, but that's the legend that goes with Archimedes. Archimedes was a very, very um, brilliant scientist of old. Anyway, so this is important. An immersed body is buoyed up by a force equal to the weight of the fluid it displaces. Notice it doesn't say anything about the weight of the immersed body. The buoyancy, the force of buoyancy is equal to the weight of the fluid that the body displaces. Okay, oops, I went in the wrong direction. There we go. The apparent weight of a submerged object, weight out of water, is minus the buoyant force. The apparent weight of a submerged object is its weight out of water minus the buoyant force. So here's an example. Here's a three kilogram block, and it's you can see it on the scale, 3 kilograms. Here there's 0 kilograms because there's nothing in it. So if you submerge this in water, all of a sudden it goes to 1 kilogram, and this water displaced goes to 2 kilograms. So you can notice, oops, I'm sorry, you can notice that the total weight, 3 plus 0 is equal to 3, and 1 plus 2 is equal to 3. So the amount of water that this object displaced is equal to 2 kilograms. Okay. On which of these blocks submerged in water is the buoyant force the greatest? 1 kilogram of lead, 1 kilogram of aluminum, and 1 kilogram of uranium, or they're all the same. Now, of these objects, aluminum is the least dense, so it's going to take more aluminum to get 1 kilogram than it would take to get 1 kilogram of uranium or 1 kilogram of lead. So since the aluminum would be larger, it's going to displace more water, so the buoyant force would be greatest on the aluminum. The aluminum block has the greatest volume because aluminum has the smallest density. Since it displaces more water, it experiences the greatest buoyant force. Okay. When a fish expands its air bladder, the density of the fish decreases, increases, remains the same. Well, if his weight stays the same, but if he's filling the air bladder, he's expanding his volume, so his uh, density has to decrease. There it is. He decreases. The fish becomes larger, but retains the same mass. Thus, its mass density becomes smaller. Okay. When a fish makes itself less dense by swelling to a larger size, the buoyant force acting on it, when a fish makes itself less dense, um, the the force acting on it, if it's less dense, that means its volume increases, so the buoyant force has to increase. If he if he's displacing more water, so the buoyant force increases. When a fish decreases the size of its air bladder, the density of the fish, um, if it's decreasing, am I doing? It seems like I'm doing the same one over and over. Okay, it increases. Okay, when a submarine takes water into its ballast tanks, its density, uh, if it's taking in more water, it becomes more dense. Um, well, so its density increases. Okay, when a submerged submarine expels water from its ballast tanks, its density decreases. Okay, this is how a submerged submarine is able to surface. It has the ballast tanks that either bring in water, or if it brings in water, it'll go further in the water, and if it expels the water, it'll raise to the top. Okay, and that's the end of part 3.